Hello and welcome to the session 9 of the Theory and Application of Network Coding course. In this session we will be talking about networks with cycles. So far in the class we considered a network without cycles, such as a cyclic, means a cyclic network, such as network depicted here in the left. For such networks, the capacity of such networks is equal to the minimum size of a cut that separates source from each of the terminals. And for such networks to achieve capacity, we don't need to mix packets across rounds of communication. So even if we have to use this network multiple rounds, we can consider each round separately. For example, if we want to send A and B during a particular round, we can do it by using this code depicted here, right? And in this code, all those packets will be in one round of communication, and we use each of the link here only one time. So let us now consider a network with cycles and network depicted here in the middle. This network still contains a cycle, what we call topological cycles, but we still be able to achieve its capacity, which is 2. So we will be able to send 2 packets to both terminal T1 and T2 by considering each round of communication separately. So for example, here if you want to send A and B, again we can send it using the code depicted here, and without considering multiple cycles, but just consider code that can be used in this cycle. So some of the networks with cycles, we will not be able to achieve their capacity without mixing packets between different rounds. So for example, consider this network depicted here on the right. And we note that for this network, the minimum capacity of a cut that separates source in each of the terminal is also equal to 2. For example, we can find 2 disjoint paths from S to terminal T1, and also we can find 2 disjoint paths from S to terminal T2. So one path will go this direction, another path will go this direction. So in this network, as we will show later, we can still achieve capacity. Capacity of this network is still asymptotically 2. So if you're using multiple rounds of communication, we can send 2 packets per time unit on the average. However, we'll not be able to achieve this capacity with just using a single round. So we need to consider multiple rounds, and we need to find a scheme that mixes packets among multiple rounds. To see this, let us show that it's impossible to do it by just considering single round alone. So suppose we're trying to do this over a single round to send packet A and B. From the source node, those packets will be forwarded by those intermediate nodes. And once we reach those nodes, we need to decide what we want to do. So we cannot, for example, this intermediate node must send a combination of packets received from both of its incoming links. If it doesn't do this, one of the paths, disjoint paths, will be not used, right? So we'll be reducing capacity, because effectively, if you're not combining packets received from 2 incoming links, we're not using one of the links. This will result in removal of this link in the network, which in turn violates the min cut. So now those 2 nodes, we have a deadlock, right? So because for this node, suppose this is node V1 and that's node V2, for node V1 to combine packets, we need to wait from the packet sent by V2, because the packet transmitted on this edge depends on the packet transmitted on the outgoing edge of V2. So similar for node V2, node V2 must combine packets received over incoming links. Otherwise, again, one of the links effectively is removed, which will result in violating of a min cut condition. So now node V2 depends on node V1, because one of the links from one of the incoming links to V2 depends on the packet sent on outgoing links of V1. So you'll see here that it will not possible to do it over just a single round, because we arrive at a deadlock condition. The basic question is, we know that for a cyclic network, we know that capacity of the network determined by the size of a minimum cut between source and each of the destination nodes. And the fundamental question we can ask for network of cycles, can we do the same? And the answer is yes, we can do it asymptotically, but only if we mix packets between multiple rounds of communication. So for certain types for networks with cycles, we can show that it's possible to achieve this capacity even if there exists a topological cycle as in this network on the left. And it can be done by just showing that for each round of communication we can transmit packets which is equal to the capacity of the network, right? In this case 2. So again, we describe this network to the left, network to the right. We can also propose a network code, so it has the cycle in the middle. However, this cycle doesn't prevent us from being able to use just a single round using the code depicted here, right? So we send A and B is forwarded to those edges, and B is also forwarded, so this node will combine A and B and produce a combined packet. So example A XOR B, if we're working over a field of GF2, it will be corresponding to addition over this field. Now this node will just forward A on this interface, and on the second interface, second outgoing link, it will just forward the packets arriving on a separate incoming link. So what we'll see that this intermediate node, so suppose let's denote it V1, so this node basically performs two operations. For one outgoing link, that's forwards packet received over this incoming link, and for second outgoing link is forward packet that arrives on a separate incoming links. So we'll see that logically, which is physically it can be the same node, but logically we can separate this node into two parts. So this is one part of this node and this is another part, right? Because again, this node performs two functions, forwards A over this link and forwards A XOR B over this link. So what we see, even if we have a cycle and topological cycle, we can logically separate those two nodes and eliminate cycles. Therefore, we can still send those two packets in a single round. Unfortunately, this is not possible in a general case, and this can be demonstrated by using this network. So this network we can already discussed, and it can be seen as a real cycle, right? So not just topological cycle, but cycles that we cannot overcome by just doing separating functionality of a node, right? So dividing node into two logical nodes that will perform several operations. However, the good news, we can still achieve this bound in an asymptotical way, and this can be done by using code presented in this slide. Our purpose is to show that the code depicted here will allow us to send 2n packets in n+1 rounds, which will allow us asymptotically to achieve the capacity of this network, which is 2. So we will be able to send very, very close to 2 packets per round. We can achieve as close to 2 as possible. So when n goes to infinity, the limit is equal to 2. So the code is depicted here. So we'll do code will perform differently for the first round and with subsequent rounds. So in the first round, we'll see that source node S will send packet A1 and over this link to V1 and send packet B1 on the link to V2. V1 and V2 will forward those packets. So V1 will send A1 to T1 and A1 to V3, and node V2 will forward B1 to V4 and B1 to T2. So we'll see that the scheme in the first round, X1 is equal to A1 and Y1 is equal to B1. So node V3 will just forward A1 over this link to V5. So this link will send A1, and node V4 will forward B1 on the link to V6. So in the first round, if we see what destination receives, we see that destination node T1 receives A1 in the first round, and this because it actually receives 2 copies of A1 in the first round, and destination T2 will receive 2 copies of B1. So it will receive B1 from V2 and also will receive B1 from the link from V6. So let's now see what happens in the second round. So in the second round, the destination will send B1, A2 and B2 on the links to V1 and V2. So nodes V1 and V2 will forward A1, A2 and B2 respectively. So A2 and B2 will be sending over those links as I'm showing here. So now what happens to node V3? So node V3 will see that in the second round, So the packet transmitted by node v3, which is vx2, it will be equal to the packet that received from v1, so it will be equal to a2, but we will be adding the packet transmitted by node v6 in the previous round. So in the previous round, this packet v6, node v6 will forward packet b1. So it will be equal to y1, which is in turn is equal to a2 plus b1. So this is what will be sent by node v3. So this packet will be a2 plus b1. Right, now this packet will be forwarded by node v5. So we'll have a2 plus b1. So the destination node will be able to get on the second round. So this was in the first round. For this destination on the second round, it will be able to get a2 and also will get a2 plus b1, so it will be able to decode b1. The same happens to terminal t2, so it will receive b2 over this link, over link from v2, and also will be able to receive different packet, right? So let's see what it will receive from v6. So v6 will be sending, so node v4 will be combining, okay, the packets transmitted by node v4 will be equal to y2, which is b2 plus what is sent in previous round by x, right? So it will be x1. And now this will be equal to b2 because in the previous round x1 was equal to a1, so it's b2 plus a1. And this will be forwarded, right? So this will be value of y2. And this is exactly the same packet will be sent over by node v6. So packets b2 plus a1 will be transmitted. So now the destination node T2 will be able to decode B2, but also will be able to decode A1. So we'll see if we analyze it further, we'll see that at each round, the destination node will be able to get, for example, T1 will be able to get A3 and will decode B2, and destination node T2 will be able to receive B3 and A2. So in each round, we will be able to decode packets that will be transmitted from the previous round. So we'll have certain delay until we are able to decode everything, but still asymptotically we will be able to receive all of the packets. So now this is basically table specifies packets that can be recovered by terminal T1 in each round. And again, as I mentioned, so each of the rounds, for example, in T4, we'll be able to recover all packets which are sent at round in the previous round T3, but also we'll get A from A4, right? But we'll not get B4, we'll get it in the next round. So asymptotically, we'll be able to receive 2 packets, and the asymptotic capacity of this network is equal to 2.